This is the overview for Week 9. This week we'll be discussing quality systems. So we're continuing our look at quality management by focusing on how risk is managed. And we'll be covering two complementary methods: the failure mode and effects analysis and root cause analysis. Quality risk management is described in the ICH Q9 documents. Quality risk management is an essential, integrated part of the quality systems. The evaluation of the risk to quality should be based on scientific knowledge and ultimately linked to the protection of the patient. The level of effort, formality, and documentation of the quality risk management process should be commensurate with the level of risk. Quality risk management process consists of well-defined steps which, when taken in sequence, support better decision-making by contributing to a greater insight into risks and their impacts. It includes elements such as risk identification, risk assessment, mitigation, elimination, and communication. As we discussed earlier, there are multiple steps involved in the biomanufacturing process. First is the design of the process. That includes the input, all the raw materials, cell lines, and the like, the process which these materials undergo, which ultimately yield your product or the output. Quality, it can be measured at each of these steps. First, as we initially talked about, design quality or quality by design. The others are controlled by dimensions of quality or conformance to quality. Quality is a relative term, often based on the consumer's perception or the degree to which a product meets consumer expectations or needs. Manufacturers have long recognized that products can meet specifications and still fail to satisfy customer expectations due to errors in design, flaws induced by the manufacturing process, the environment, product misuse, not understanding what the customer wants or needs, and other potential causes. There are several key issues in the production of biologics. First, there are biological variations in the production of materials. These can result from animal-to-animal variations or cell culture variations, which can result from differences in the cells or cell populations and differences in culture conditions. There are biologic safety with the introduction of unknown pathogens or unrelated impurities with unknown activities. However, regardless, it's important to remember that the greater the number of biological variables, the greater the need for process analytical technologies, which we discussed earlier. In the field of quality, there are three important individuals, or gurus. First, W. Edwards Deming is considered to be the father of the quality movement. He brought a scientific approach to quality and quality assessment. Joseph M. Juran outlined quality by design, focusing on quality and innovation as one of the three universal pathways. And Philip Crosby, who wrote Quality is Free, to explain the definition of quality to executives in terms they could easily understand. His book addressed the misconceptions of quality management. In 1986, Deming wrote the book Out of the Crisis. In this text, he stated that quality is uniformity and dependability. He focused on the use of statistical process controls and other statistical tools for quality management. He outlined his 14 points, and most importantly, he presented the PDCA method of quality control, which is plan, do, check, and act. In developing quality by design, Juran had a trilogy of quality. Managing for quality consists of three basic quality-oriented processes: quality planning, quality control, and quality improvement. The role of quality planning is to design a process that will be able to meet established goals under operating conditions. The role of quality control is to operate and, when necessary, correct the process so that it performs with optimal effectiveness. And the role of quality improvement is to devise ways to take the process to unprecedented levels of performance. Philip Crosby developed 14 steps as a foundation for quality management. His absolutes for quality management were: quality means conformance, not elegance. There is no such thing as a quality problem. There is no such thing as the economics of quality. It's always cheaper to do the job right the first time. The only performance measurement is the cost of quality, and the only performance standard is 0 defects. What is quality management? Quality management ensures that the project will satisfy the needs for which it was undertaken. Quality management processes include planning quality management, identifying which quality standards are relevant to the project and how to satisfy them, performing quality assurance, periodically evaluating overall project performance to ensure the project will satisfy the relevant quality standards, and performing quality control, monitoring specific project results to ensure that they comply with the relevant quality standards. So how does quality management come into play when failures occur? Well, it addresses why did the failure or problem occur? Symptoms versus causes. For causes, investigate the whole process: suppliers, component failure, design, manufacturing, changes in management. Why were the causes not detected? The goal of quality management is to find problems, not to fault find or to provide criticisms. Finding problems is a creative act. It is the same as innovation. We should never stop at only finding problems, but also develop a systematic corrective action plan. That is, fix the process that created the problem and identify detection algorithms. We should never forget that every job should relate directly to improving a product. Everyone should readily accept help from review participants. Some of the common quality improvement processes are the model for improvement, or the rapid cycle quality improvement method, or the Deming's process of PDS or CA, and failure, modes and effects analysis, and root cause analyses. So how does the cycle quality improvement process work? First, define the problem. Identify and carefully describe what it is that you really want to improve, such as the source of the problem you are confronting. The cycle involves plan, do, study, act, so-called the Deming wheel. It is circular and a never-ending problem-solving process. And the 7 tools for quality controls. These are tools typically taught. So how does this circular quality control process work? Well, first, there's plan. Evaluate the current process, collect procedures, data, the problems. Develop an improvement plan and performance objectives. Then you implement this plan on a trial basis. You study. You collect data and evaluate against the objectives. And last, act. You communicate the results from this trial process, and if successful, you implement a new process. Shown somewhat differently as the Deming wheel, this PDSA cycle involves plan, define the problem, and develop the plan for improvement. 2. Do. Implement this plan on a test basis. 3. Study or check. Assess the plan. Is it working? Is the problem solved? And act. If the problem was solved, institutionalize the improvement and then continue the cycle for future problems. One of the earliest methods for identifying the causes of failures or problems was termed the failure mode and effects analysis. Failure modes and effect analysis is a systematic, proactive method for evaluating a process to identify where and how it might fail, and to assess the relative impact of different failures in order to identify the parts of the process that are in most need of a change. The failure modes are the ways in which the process can fail. Effects are the ways in which these failures can lead to waste, defects, or harmful outcomes for the customer. The failure modes and effect analysis is designed to identify, prioritize, and limit these failure modes. This approach is not a substitute for good engineering. Rather, it enhances good engineering by applying the knowledge and experience to review the design process of a product or processes to assess its risk of failure. There are two broad categories of the failure modes and effects analysis, which is the design and process effects. Well, why perform the failure modes and effects analysis? The sooner a failure is discovered, the less it will cost. If a failure is discovered late in the product development or launch, the impact is exponentially more devastating. The failure modes and effect analysis is one of used to discover this earliest possible point in the product or process design. Discovering a failure early in product development using this approach provides the benefit of multiple choices for mitigating the risk, higher capability of verification and validation of changes, collaboration between the design of the product and the process, and ultimately lower cost solutions. The failure mode and effects analysis includes the review of the following steps. Failure modes, answering what could go wrong. Failure causes, why would the failure happen? And failure effects, what are the consequences of each failure? To perform a failure mode and effects analysis, first, describe the product or process and its function. 2. Create a block diagram of the product or process. This diagram shows the major components or process steps as blocks connected together by lines that indicate how the components or steps are related. 3. Use the diagram to begin listing items or functions. 4. Identify failure modes, defined as the manner in which a component, a system, a subsystem, or process potentially fail to meet the design intent. And 5. Identify the causes for each failure mode. A failure cause is defined as a design deficiency that may result in a failure. The potential causes for each failure mode should be identified and documented. The failure mode and effects analysis should begin with a block diagram for the system or subsystem. The diagram should indicate the functional relationship of the parts or components appropriate to the level of analysis being conducted. Another approach for managing or analyzing problems and failures is termed the root cause analysis. This is a way of looking at unexpected events and outcomes to determine all of the underlying causes of that event and recommending changes that are likely to improve them. The process for identifying contributing or causal factors that underline variations in performance associated with adverse outcomes. The root cause analysis is a derivative of the failure mode and effects analysis and has been used by the U.S. military since the 1940s. It's used by NASA in the 1960s for the Apollo space program and by U.S. manufacturing in the 1960s and 1970s. In the 1990s, the U.S. auto industry adopted the failure mode and effects analysis standards. The goals of the root cause analysis are to find out what happened, why did it happen, what can you do to prevent it from happening again, and how do we know that what we changed made a difference. This also incorporates the 5 whys, and it utilizes the cause and effects diagrams or a fishbone diagram. Cause and effect diagrams trace complaints about quality problems back to the responsible production operations. They help you find the root cause of a problem. It is also known as a fishbone diagram. And you could also use the 5 whys technique, where you repeatedly ask the question why to peel back the layers of symptoms that can lead to the root. So the cause and effect diagram, or fishbone diagram, the purpose is a visual display of information to identify root causes rather than symptoms. To construct a fishbone diagram, you determine the issue and write the problem statement in a box at the right of the diagram. Find the main causes and write them on the branches flowing to the main branch, whether it's method, equipment, personnel, material, environment, customer expectations, money, management, or government regulations. Identify all possible causes and write them into the diagram as subcauses in each category. The typical application determines the real cause of the problem and checks the potential effects of a solution. This slide shows a simplified version of the cause and effect diagram. It shows you the quality problem in the box at the end of the diagram and the various components that could lead to those problems, whether it's suppliers, workers, machines, the temperatures, the process, or materials. The root cause analysis model focuses on prevention, not blame or punishment. It focuses on system-level deficiencies rather than individual performance. It entails communication, training, scheduling to prevent fatigue, environment, equipment, rules, policies, procedures, and other barriers. As part of the root cause analysis is a decision-making tool called the Safety Assessment Code. The Safety Assessment Code provides a score that is a risk estimate that considers all the actual and potential consequences of a situation. Close calls can point out system-level vulnerabilities as powerfully as actual events. All events, actual and potential, with a safety assessment score of equal to 3 requires a root cause analysis. In summary, quality management. Quality is required at all times by everyone end user's perspective. Quality management addresses issues upstream and addresses product and process defects at the design stage. It requires fixing problems by fixing the systemic process issues that cause the problem. It focuses on implementation. So as we think about bioprocessing and how we detect failures and other issues in the pathways, we need to remember that quality improvement is a process, not an event. And there are no secrets to success. It is a result of preparation, hard work, and learning from failure.